We can even see like here we get all these normals. So when there is a change, like a big change here in the scene, we can see like the normals here is pointing out. Hey guys, and welcome to a new video in this computer vision tutorial. So in this video here, we're going to talk about point clouds with the Open3D framework or like library that we talked about in the last video. So in the last video, we had a short introduction to what this library here is actually like capable of and how we can use it in Python and how we can actually like display and do operations with point clouds. But first of all, remember to join the Discord server. I'll link to it down in the description here. You can join the channel, chat with us about computer vision, deep learning, AI, and so on. You can also become a member of the channel here if you want to support the channel with a small monthly fee, and everything will go to create more and better quality content. So thank you guys. So first of all here, we're just going to go through a couple of slides that we're going to look at in this video. So in this video here, at the end, we're going through some of the tutorial examples that we have provided by Open3D. So we can see how we can actually load in a point cloud, do different kind of operations with it, and so on. So we're going to use those tutorials. But first of all, I want to talk about some of the operations that we're going to do, what the operations does, and then again, we will do it in code later on. So first of all here, we're going to talk about voxel downsampling. So when we have a point cloud, we have like a number of different kind of like points in our point cloud, and sometimes we have a lot of different kind of points and also some outliers and stuff like that. Then we can actually use voxel downsampling to downsample our point cloud. So we have less points, but we still have a really good representation of our environment or like objects that we actually like have that point cloud of. So the idea behind voxel downsampling is that we're looking at different kind of like boxes. So we have these voxels, what we call voxels, which is basically just boxes around in the point cloud. And then when we look inside of that box, then we actually pass into the function the size of that voxel that we want to create. And then we just have a number of voxels inside of a whole point cloud. And then we look inside of that voxel and take all the points in that voxel, and then we combine that to a single point. So it could either be like the center of our voxel, or it could be like the mean position or like the average position of those points that is within that voxel, or like that bounding box, if you can say it in that way. And then we will actually like downsample our point clouds, as we're going to see. So if we have a really dense point cloud, we can actually use voxel downsampling to downsample our point clouds. So we have like a cleaner and better representation without that many points in our point cloud, because the more points we have, the more processing power and computational cost it takes to do more operations. So often we actually start by downsampling our voxel or like our point clouds and do those post operations first. So the second thing I'm going to talk about here is voxel normal estimation. So after we have downsampled our point cloud with voxel downsampling, we can actually like compute or like estimate the normals to all the points in our point cloud. So right now we only have information about the X, Y, and Z coordinate of the point clouds, or like the points in our point clouds, and we can also like add additional attributes, like for example RGB channels. So for colors, so we both have a point cloud with the corresponding colors to each of the points, so we can then reconstruct our whole scenes from our point clouds. But then another important information is also to estimate the normal to all the points in our point cloud, because then we can use that to actually like see how the objects are actually like orientated around in the environment, and we can also do segmentation with normal estimation. So down here we can see an example of normal estimation on the downsampled point cloud with voxel downsampling. So we can see all these different kind of like lines here, or like errors, which is just the normals from like the objects. So this will just be the direction that those points is actually like pointing in. And we can see here at the chair, like a lot of the errors is actually like pointing out towards us, and also at the wall here. So we can just use this information here to actually like segmentate out different kind of things. So we can see here we have this chair in the middle, then we have some windows over here to the left where there's a lot of changes in the normals. We can also see like this desk here down at the bottom, and also the painting at the wall at the top right corner. So we can use these normals to do a lot of different kind of things. So after we've downsampled our image, we should actually like do this normal estimation. And again, I'm going to show you in code how we can actually like do it. It is really easy by using this Open3D library. We're just calling a function and it will do everything for us. And this will just be the return that we can then use later on for like more processes or like more operations on our point clouds. So before we jump into the code and the example that I'm going to show you in this video, we're just going to open up the documentation for Open3D, so we get familiar with it, how we can operate around with it. We can see the tutorials, the functions, and we can even see like documentation for those functions, what they do and like how they implement it and stuff like that. So we know a bit more under the hood what we're doing, because when we go into code, we actually like just load in our point cloud, call these methods or functions on our point cloud, and it will do everything for us. So here we're just at the start page here. We just get the same introduction as in the introduction video that we had. We have all these different kind of things here within the start here. It was the same on GitHub. But over here to the left, we can see all the different kind of like tabs that we have, or like the menus. So we have like, for example, some tutorials here that we're going to go through in the next couple of videos. We also have some C++ API documentation and Python documentation. So again, this both works in C++ and Python, and we're going to we're going to have code examples where we both do it in C++ and Python if you prefer like C++ over Python, or you have created your computer vision application in C++ and you just want to keep using that by processing your point clouds in C++ as well. But first of all, we're going to focus on doing it in Python and just going over these examples. So first of all, here in this video, we're going to go through or like look at this geometry tutorial. So the first one we're going through here, we see we get a lot of different kind of like sub tabs here. So we have a point cloud, we have meshes. So we're going to talk about like point clouds and meshes. What is the difference? How we can create meshes from point clouds. We have some RGB images. So how we can use depth cameras with color channel images as well to create our like point clouds, do point cloud processing with that, and so on. So we can create a really we can create some really nice applications and projects with this library here by just using these things. We also have some point cloud outline removal, which is often the case that we have. So we want to do that. We also have this voxelization here, where we can do the voxel downsampling, voxel normal estimation, and so on. Over here to the right, we can also see like all these basic things. So what these tutorials here, or like what these tutorials inside of this geometry class here does. So first of all, we're going to talk about point cloud, so how we can visualize point cloud, voxel downsample, vertex normal estimation. After we have downsampled our point cloud, we can crop our point cloud, paint the point cloud, get a distance between points in our point cloud as well, and we can do a lot of different kind of things. And then in the other videos, we're going to go more into details with the other stuff down here, where we can see like how we can actually like do like crop and mesh, how we can use meshes instead of point clouds, and we can do a lot of different kind of things. So we can actually like apply filters on top of our meshes as well. So we have average filters, Laplacian filters, and so on. But if we just go up here and again go into this point cloud basic tutorial, we get here a short description of what this this tutorial here demonstrates, or like what it does. We can visualize a point cloud in this way. It actually gives us an example as we're going to go through in the code as well. And we can just see all these things here. So now we're open up a Jupyter notebook here with the code examples that I just showed you from the documentation, and is also stored in like if you download the zip file from the GitHub. So we can see this tutorial here where we're just going to import Open3D as O3D. Here we're going to import NumPy, Matplotlib, and so on. And here we're actually just setting up this tutorial like Open3D tutorial as well, so we can actually create this interactive visualization window that we're going to see when we actually run our point cloud, so we can play around with it in 3 dimensions, and then we can rotate around, see the point clouds from different orientations, zoom in and out, and so on. So here we can see we have this point cloud. So this tutorial demonstrates basic uses of a point cloud. And first of all, we're going to visualize a point cloud. So the first part of the tutorial reads a point cloud and visualizes it. And again, we're just going to use the data or the point clouds that is already provided by Open3D. So these are just some example point clouds. You'll just, if you have your own point clouds, you can use those as well. We're going to create our own point clouds as well and going to pass them into these functions and do operations on that as well later on. So here we're just going to use this o3d.io, and then inside of the IO module, we have this read point cloud. This is basically just a function where we pass in the path to our point cloud that we want to load in. This file here can contain all the different kind of information about the X, Y, and Z coordinates, and also the RGB colors if we have that assigned to a point cloud as well. Then we're just going to print out the point cloud that we created, and also the individual points in our actual point cloud, so we can see our X, Y, and Z coordinates. And then down here inside of this visualization module in Open3D, we just have this draw geometries function or method here implemented, where we just pass in the point cloud. This is actually the only parameter that we need to pass in to be able to run it and play around with it. But we can also set these factors up here if you want to start with like a default view of our point cloud. It's not really necessary, but it is just so we don't have to zoom in and out and rotate the object around. So we have the initial view. So if you're going to run this first one here, so first of all we need to import them, and then we can go down here and actually like load in our point cloud and visualize it. So this was the same as you saw in the last video. So we get this point cloud here of the chair, the desk, and like the TV or like painting up here at the wall. And then we can just rotate the point cloud here around with the mouse. We can hit minus here as well, so we get like a denser point cloud. And we can also hit plus here, so we get like a smaller point in a point cloud if we want this representation instead, and see like what is going on, where are we missing some of our points and stuff like that. But if you just want to reconstruct our environment, like this looks pretty good when we have like a more denser point cloud in our image view. So this is how we can load in a point cloud and just display it with one function. So we use one function to load it in, and we use one function to actually like draw it. And this draw geometries here is the function that we're going to use like every time we have done an operation. We're just going to use the exact same function here to actually like draw the point cloud in this interactive window. So here we can just read like what it does here. So read point cloud, read the point cloud from a file. Everything here is just what I said. So now we can go down to the voxel downsampling, where we actually like uses, we can see here voxel downsampling uses a regular voxel grid. So we have this voxel grid with all of these voxels or like bounding boxes inside of it to create a uniformly downsampled point cloud from an input point cloud. It is often used as a pre-processing step for many point cloud processing tasks. The algorithm operates in 2 steps. So first of all, we have the points are bucketed into voxels. So as I said, that we have these different kind of like bounding boxes, and then we look at all the points inside of those bounding boxes, which is actually like voxels. And then each occupied voxel here generates exactly 1 point by averaging all the points inside. So this algorithm here actually like takes the average of all the points, and then that will be the new position of only 1 point. So we could actually like have 10, 20 points inside of our voxel if we have a really large voxel grid, and that will produce only 1 point with the position of the average of those 10 to 20 points inside of that voxel. We could also change the algorithm, so we actually like just take the center of our voxel and stuff like that. But the average here is actually like often used. It takes a bit more computational cost, but it doesn't really matter in the end if you're just running it here offline. And we also use the cloud here. So Open3D actually uses the cloud, so the processing is really fast when we're using these functions here, and it's also implemented in C++. So this is just a Python API built on top of that. So here we have an example. We're just going to call this PCD, and then we can just, so we're just inside the point cloud here, we just have a function or like method implemented that is called voxel downsample. And the only parameter that we need to specify is the voxel size. So this will be the size of our voxel or like the size of our bounding box. And then we just have a grid of all of those voxels that we're going to look at for each of the points, or like for all the points inside of those voxels. Again, we're just going to use draw geometries to draw it. So now we're going to actually like see the downsampled point cloud here. So if we just go up here at the top, so this was our original point cloud, and then we just took this voxel downsampling, and then we downsampled our image or like our point cloud down to this representation here. We can see we still have all the information in our point cloud, but instead we have like 200,000 points here. We have now reduced it to like a lot smaller number of points here in a point cloud, but we still get a really nice representation, and we can still use this for a lot of different kind of things. We can still hit plus and minus here to make it like denser or like thicker, all of the points in our point cloud, and we still have a really nice representation. We can still see the desk. We can see we have something on the wall here like a painting, and we can also fairly nice still see the chair here in our image, even though we have reduced the size of our point cloud by a huge factor here by having this voxel, by running this voxel downsampling algorithm. And this is really good by using this for pre-processing as it states up here, because then we don't have that many points in our point cloud that we need to do operations on later on. We still have the same information, but we can do our operations way faster later on. So one of the last things that I'm going to show is the vertex normal estimation. So after we have downsampled our point cloud, we can then do normal estimations on those points. So again, if you have a larger point cloud, it will take longer time, more computational cost to actually calculate these normals. So do the voxel downsampling first if you have a really dense point cloud. So another basic operation here for point cloud is point normal estimation. Press Enter to see point normals. The keys minus and plus can be used to control the length of the normals. So here we go again inside this downsampled PCD. We have this estimate normals. We just call estimate normals. The search parameters here we set equal to this KD tree search parameter hybrid here. So just need to specify the radius and the max nearest neighbors. So this is just the parameters that it takes to actually calculate this normal estimation. If you want to know more in details what these things here does, go into the documentation. There's a short description of like what this function here actually does, or like what the algorithm does and why it needs to take in this radius and the maximum number of nearest neighbors that we want to look at when we're doing our normal estimation. Because when we want to do our normal estimation, we want to see like the different kind of like neighbors and how that is changing from the scene to scene, so we can actually like segmentate out objects in our point cloud, as we're going to see when I run this function. So here we can see the normals. We can even see like here we get all these normals. So when there's a change, like a big change here in the scene, we can see like the normals here is pointing out. We can see the top of the chair here, then the normals is actually like pointing out, and we can see here at the wall they're pretty consistent. They're just pointing directly towards us because they're just perpendicular to the wall here, the normals for the points in our point cloud, and the same goes for the floor and also just like straight surfaces. So it's more on the curves here, like on the table here, or like the chair. So we have all of these like, so when there's like an edge in the point cloud here, we will get these like sort of like strange normals that's just pointing in sort of like kind of weird directions. So it's just perpendicular to the surface, these normals that we're estimating. So the last thing that I'm going to show you here is how we can actually access these estimated vertex normals. So after we've estimated them, we can see that these estimated normals can be retrieved from the normals variable of PCD. So now we're not only storing the R, G, and B values together with our X, Y, and Z coordinates for our point cloud, but we're also storing the normals for each of our individual points, because we can actually use the normals to do post estimation of different kind of objects in our point cloud later on, as we're going to see as well. So we'll just add another attribute here to our point cloud, so we just have as much information about our points as possible. So that is also why we need to downsample it first of all, because we just keep adding information to our point clouds. And the larger our point cloud is, like the more information we need to store about each individual point, it takes up more processing power and so on. So it's really intuitive. And we still keep a lot of information even though we're downsampling our point cloud. We can still do all of our operations, do post estimation, reconstruction of our environment, and so on. So here we're just going to print a normal vector of the 0th point. So we can just go into down PCD. So this is our actual point cloud. And then we have this attribute here, which is the normal. And then we can just access each of the individual points. So we can either take like the 0th point here, or we could take the last point in our point cloud, or we can take some arbitrary number or like index of our points. So in this example here, we're just going to take the first one. So we're going to print this one here. So we print a normal vector of the 0th point. So this will actually just be the normal vector that we're actually like displaying up here. So let's say that this was the 0th point in our point cloud. Then this line here, or like this normal here, is represented by this normal vector. So we can just go in, access each of these individual normal vectors, and then we can use those later on to do actual like operations, post estimations, and so on. To check out other variables, please use help, and then we can actually like get this down PCD. So, but you don't even have to go into like the documentation of Open3D. You can just call this help function. It will show like all the attributes that is assigned to the point cloud. What information can we actually like get out from our point clouds after we've added to it. And this is really, really useful. And this is just a really nice library. I like it a lot because we can use it for a lot of different kind of things. It's really good to work with, and the documentation is so good as well. So normal vectors can be transformed as a NumPy array using NP as array. So we can actually like convert those or like transform them to NumPy arrays. So we can use NumPy to do operations or like further operations on our normal vectors, which is often the case that we want to. So print the normal vectors of the first 10 points here, and then we're just going to convert it to a NumPy array. So we have this downsampled PCD, so our point cloud. Then we take all the normals for the first 10 points, and then we just convert it to a NumPy array. So now we're just going to print it out here. So we're printing out the normal vectors for the first 10 points, and it will be stored in a NumPy array, so we can do operations with it. We can do like multiplication, all these different kind of things that we know from NumPy, which we're going to use when we're going to do, like, for example, post estimation, segmentation and stuff like that in reconstruction of our environments, where we want to know like or where we want to like use the information about our normals from our point cloud. So here we can check out working with NumPy for more example regarding NumPy arrays. So this will just be the documentation for NumPy, so we can see what operations can you actually like do on NumPy arrays. So basically these normal vectors. So thank you guys for watching this video here. We've been through like how we can load in a point cloud. We saw the documentation. We looked at some of the theory behind how these operations actually like works on the point clouds and the algorithms, where we looked at how we can downsample a point cloud if we have a really dense point cloud and still keep the representation fairly good. How we can do voxel downsampling and then use that to estimate the normals to all the points in a point cloud. How we can add additional information to our point clouds, and also how we can access each of the individual attributes that we can then use later on to do more operations on our point cloud. So thank you guys for watching. Remember to hit the subscribe button and bell notification under the video so you'll get a notification when I upload a new video in this tutorial. Also remember to like the video if you like the content and you want more in the future. It just really helps me and your channel out in a massive way. I'm currently doing this computer vision tutorial where we're talking about basic image operations. We're doing camera calibration with stereo vision, monocular cameras, and so on. And now we're actually like both combining all these things together using stereo vision to actually like create point clouds, and then we can use those point clouds with this Open3D 3D library, which is just really amazing. And we're going to create a lot of videos about that because it's just really nice. It can be used for real life applications. And again, I'll link to the tutorial up here if you want to check that out, or else I'll just see you in the next video, guys. Bye for now.